and some problems. We'll do a couple problems together that require hash tables to solve them. So, an introduction. A hash table is a data structure that uses a hashing algorithm to decide where an element will be stored in it in the table. So, I'll explain that a little more in the next slide, but a hash map is just a specific implementation of a hash table, and it's only in certain programming languages, but a lot of the big ones are going to have it. And a hash map, like a hash table, is going to store a key, and then it's going to hash that and store values associated with that key, and it's going to decide where it's going to be placed based on that hashing algorithm. So in Python, if you're familiar with a dict, that's the implementation of a hash map in Python. So how they work. It maps keys to values using a hash function. It converts a key into an index in an underlying array. And then so operations like insertion, deletion, and lookup are O1. So basically, you have, this is just like an example hash function. Obviously, hash is a function that you're passing it into, but you're going to find out the index of where it needs to be placed in the array by passing in the key to a hash function and modding by how big that array is. And of course, because hashing algorithms aren't perfect, you could have multiple things hashed to the same thing because you're modding by a certain table size. So pigeonhole principle would say that eventually you're going to have something collide. So there are two main strategies that are employed when you're trying to handle collisions. The first one is going to be chaining. So the way chaining works is at each index, it's going to use a linked list. So when you index something that's already been indexed, so it has the same hash as something else, you just connect it to that one in just a linked list format. And linear probing is going to jump to the spot where the hash says it should jump to, and then sequentially after that, it's going to find the next like open spot and put it there. So I can explain that using like a little diagram.
Can you go back to that last page and it's all of your notes?
No. So with chaining, we're going to have something like, so say, just for the sake of simplicity, this is my table, and each of these are entries. So this is going to be index 0, 1, 2, 3, 4, 5. So when I index, or I hash something, so say my key is, I don't know, ABC, and I pass it in my hash function, and I get 2. Then I'm going to put ABC here. Then say I have CBD, and that's going to pass in, and I'm going to get 5. So I'm going to put that here. And then I'm going to pass in maybe ACD, but maybe that'll also spit out 2. So what's going to happen there is because each of these indices or each of these spots in the array is a linked list, I'm just going to extend this and link it to another spot that contains ACD. And so that's how collisions are handled. Obviously, this is not going to be perfect because if your hash function is really bad, maybe everything hashes to 2 and you just have a linked list. So you got to make sure your hash function is good so it's evenly spread out. And linear probing is a little different. So I'll have the same starting ones here. So we had ABC going here and CBD here. But in the case where I get another hash, another key that hashes to the same index, which would be 2, instead of like chaining it, I'm just going to move to the next available slot down. So in that case, it would be 3. So I would put ACD here. And this also isn't perfect because eventually it's going to get filled up. But these are just 2 different ways of handling it. And yeah. So again, like I said, the hash function matters a lot because if you're just using like a simple, like adding up all the ASCII values or something, there's going to be a lot of combinations of letters that are going to give you the same hash. And so you're going to have a lot of collisions, and that slows down the hash map a lot, which kind of defeats the purpose of it, because like I said here, the insertion, deletion, and lookup are O of 1, because the only thing you need to do to find where something is going to be stored is just to hash the key, and it's going to immediately give you the index of it. So obviously it's going to be a little more complicated than that when the collisions occur, but at the base level, that's what we're looking for. Something that we don't have to like loop through to find where something is stored. So some common applications of hash maps, we're going to be doing frequency counting. So like counting all the elements in an array, counting how many of them are the same, that sort of thing. Duplicate detection, like I said, if an array has duplicates, that means if we take something, hash it, and something else hashes the same thing, and they're not actually, or they are the actual same value that it's hashing to, then we found a duplicate. So it's really good for that. Index mapping, again, pretty simple stuff, just like hashing and storing a key value pair. So the key is the value and the value is the index. That's kind of confusing, but yeah. And the two-sum problem, which is actually one we're going to do together. So efficiently checking if two numbers sum to a target. We'll go over that question a little more in depth. So obviously, we don't want to have to write the code for a hashing function and the implementation of like chaining or linear probing, however you want to do it every time. So these are implemented in most programming languages. In Python, it's literally just a dictionary. If you've heard of a dictionary, that's what that is, a hash map that stores this, this key that you give it. It hashes that and stores it, and it associates it with a value. And so, oh, I better plug that in. But at the base level, it's just a more advanced implementation of what I showed you with the hash table, where it's storing key value pairs. And these are used very frequently in programming. Like I use them all the time. So they're really helpful. And the syntax for them is fairly simple. You can have the curly braces, that signifies that it's a dictionary. Or you can just use the word dict with the opening and closing parentheses. And to index something in it, you just have square brackets and the key that you want to access. So in this case, I'm actually inserting something because Apple is just becoming 5 and there was no Apple in it before, so it just assigns that. But if I said under here, hash map at Apple equals 4, then it's going to change that value because it's associating it with a new value. And then to delete something, it's just del, and then the what you want to delete. In C++, similarly easy. They're called unordered maps in C++, and it's the same way you access them. It's just square brackets, and then to delete is just dot erase. So not much more complicated than the Python version. So we're gonna do a couple LeetCode problems together. The first one is going to be this one. It contains duplicate. So if you want to go to that site, we can go over that one together. Is that the right? Evidently not. Okay. Can zoom in a little bit on that. So this is marked as an easy one. So given an integer array nums, so just an array of integers, return true if any value appears at least twice in the array, and return false if every element is distinct. So a pretty simple question. First, we can think of like a naive solution, right? I could just loop through every single one of these and then just check everything after it and see if it's the same. And that would end up giving me an answer to that. So first I could check with this 1. Is there another 1 in this list? Yes, there is. So 1 occurs at least twice. And if we notice here, we don't actually it explains it with using the indices, but we don't actually need the indices. We just need to output true if there is a duplicate or false if there is not. So that makes it a little easier. But can anybody tell me maybe how we could use a hash map to solve this?
If we convert nums to a hash set, we can check the length of both the original list and the hash set and see if they're equal. If they're the same size and there's no duplicates.
Sure. Can you explain a hash set?
What?
Explain a hash set.
What do you mean?
Explain what it is.
So a hash set, so if there's duplicates, they're both gonna end up being mapped to the same hash, whatever it is. And behind the scenes, Python will basically remove the duplicate elements. So if one appears more than once, it'll be included in the hash set, but it'll only be included once. So when you convert nums to a list, or sorry, to a hash set, it's just gonna be the hash set of 1, 2, and 3. There's not gonna be any duplicates in that hash map, so the duplicate will get removed.
Okay. Yes. So similar to the definition of a set in math, a set in computer science does not have duplicate elements. So an easy way to do this is just to convert nums to a set. So now we have a set of nums, and I'm going to print out and see what that looks like. Is it gonna run? Oh, I need to log in. Awesome. Okay, back to this. Let's run that and see what it prints out. Obviously, it's not going to give us any good answer, but it is going to tell us what the output looks like when you print the set out. So as you can see here, converting it to a set removes any duplicates. So using that knowledge, we can check the length of the set of nums. So I've converted it to a set, and if that length is equal to the original length of nums, then we can deduce that it never actually removed any elements, so none of them were duplicates. And as it turns out, length is not a function in Python, but len is. So I'm used to C++, I guess. There, if we run that, we're checking if the length of the set, oh, awesome. What did I do wrong? Did I reverse the, oh, okay, yeah, I just reversed the logic. Cool. Checking if the length of the nums set that we converted is equal to the length of the original nums, which means that nothing was removed. And that means that there were no duplicates, because converting to a set automatically removes duplicates. So yeah, that one's a pretty easy one. We can submit that and see if we get the right answer. Cool. Surprisingly fast. LeetCode does that sometimes. But yeah. So that one was not super difficult, but we can move on to a slightly more difficult one called twosum. This is a pretty famous problem that actually has a pretty fun solution using hash maps. So given an array of integers nums and an integer target, return indices of the two numbers such that they add up to target. You may assume that each input would have exactly one solution, and you may not use the same element twice. And you can return the answer in any order. Okay, so can anybody think of like a naive solution to this? What I could do to find a pair of elements that sum up to a target in a list?
Try every combination.
Yep, that is indeed a solution. I could literally generate every pair in here and see if any of them add up, and then find their indices. Yeah, you could do a nested for loop. So similar to the last solution, just start with this number, loop through everything after it, and see if any of them add up to target. But that is O of n squared time complexity, and we want to do a little bit better than that. So, can anybody think of what we could do with a hash map, where you can map a key to a value? How we can solve this using that? All right. Well, maybe think about it like, what we're given is an integer array called numbers and a target, and what we need is the indices. So first, what I could maybe do is just run through something that finds all of the, or that assigns all of the indices to a, or assigns all of the indices, or all the values to their index. So I could have my an index dictionary, loop through everything in nums, and I'm setting every key that is the number in nums to its index. So what we're going to get there is a dictionary of key value pairs where each key is all of the elements of nums, and each value is where it is in the actual array. So 2 is in index 0, 7 is in index 1, so on. So from there, could anybody maybe think of what we can do with that information to maybe only have to loop through the list once and actually get the answer? All right. So first thing that I thought is you have an integer target. So if you want to find the complement of a number, so whatever your number is, how much you need to add to that to get to the target, you just need to subtract that number from target. So I'll get rid of this actually. So the complement of a number, say my target is 9. The complement of 2 is going to be 9 minus 2, or 7. So that just means, what do I need to add to that to get to my target? So maybe what we could do is loop through it once, storing the indices, but also checking if the current number we're at is, if that number's complement was already in there, that we've already found. So again, looping through all of the numbers, I can set the current index to be associated with the value of the current number, and then, because I can find out easily what the complement number is, I can just check if that complement is already in our dictionary. So if complement in index dict. So basically, behind the scenes, what that's doing is if index dict at complement. So checking if that value is associated with anything. I'm going to write it like this. because it looks more like English. I can return, looks like it wants a list of 2 indices. So I can return the I, the current I, and the stored index associated with the complement of our current value. So, and you can return the answer in any order. So either way it works. So what we can do is run that and see if we get the right answer. Looks like we did not. Okay, so looks like we forgot our base case. And also forgot this specifically. You may not use the same element twice, which is awesome. Because it looks like it got 0 plus 0. Just add that real quick to make sure that we're not using the same element twice. Just checking if it's not our current element, because that could be a problem. And also, we have to, we can assume that there is exactly one solution. So I don't have to worry about the base case of there being nothing. So let's see what we got wrong on this one. Yeah, okay, same thing. Okay, so it looks like here what's going on is it is having a problem with trying to access the same value or same key twice, but just changing it up. So maybe we'll have to change up our approach. Can anybody think of how we could edit this real quick to handle this case of the numbers being the same, but they're different indices? So we want to worry about that case.
Number maps to a list. Indices.
Could do that. Could do that. Any other ideas?
The if statement, you can also say that make sure that the indices are not the same.
So we did that already. Because the problem here isn't that the indices are the same, it's that the numbers are the same, but 0 and 1 should be the solution because they're different indices and they add up to the same thing.
I don't know if this is the best way to do it, but maybe have a variable for the number you last added. So maybe you can have like a last added set of equal to like -1 or negative whatever you want it to be. And then just kind of keep track of what the last number you added was and kind of have that in your if condition.
Sure.
Where you won't go through that extra check of index dix complement is not equal to I if your last number is the same as your current number.
Okay. You could probably do that. But the problem is, what if it was 3 and then 0 and 3? Then 3 and 3 should be a solution still, but the last added was 0. So maybe we could do something like, instead of maybe storing the value or the key being the number, maybe we could think about storing something else as the key.
What if you have a dictionary that says, okay, the complements to 2 is 7. So we have 7 as our key, and then our value at that key being what index we found that number at.
I like that idea. So we can edit this. Just comment that out. So you're saying we could do something like that, and then we could search for what in the array or in the dictionary. So we have the complement being stored here. We could search for we could do
I guess wouldn't you want to do the complement check first, maybe? Because you initialize your dictionary to nothing. There's no keys.
Mhm.
So before you do the complement calculation, I guess
I guess maybe you could do something like
if you do index dix complement equals I, you could have that check to see if that complement already exists. So before you add
you could probably do that here then. We could do something like instead of assigning it here, we could check if the complement exists first and then assign it. So let's run and see if we get the same answer with that. As it turns out, we do not. So we are storing the complement, or storing the current index and checking if the complement is in there. And so let's see if we actually get all the answers right. We did get the test cases right, but cool. 0 milliseconds, that's awesome. So that's a way that you can use hash maps to solve problems for you. And this one is a pretty common problem to solve, being able to store indices and associate them with their values, because sometimes you don't want to have to loop through a list a bunch of times. So
I'm curious to see if those extra points on the distribution, like halfway through, I wonder if those are O(n) squared solutions.
yep. Yep, this guy looks like he nested for loop, which is what we thought of at first.
What are the really long ones then?
The really long ones. Oh, he's enumerating it. I mean, it's the same thing as a nested for loop, but it just takes longer because enumerate is a function that takes a long time. Interesting. But yeah, is there any questions on that? Okay, cool. So just a quick talk about the downsides of it. Just the main thing is that it is not necessarily going to be sorted, right? Because like I showed in the example, sometimes something that you insert later is going to be stored before something that you inserted before, because they hash to something that is earlier in the table. So that could be a problem. That's really just the main one. But other than that, they're pretty easy to use because most programming languages have them by default, and they're not too difficult to understand. So they're pretty cool. So are there any questions on these? No? Okay. So there is a list of other problems on LeetCode. They use hash tables and hash maps to solve. And LeetCode so nicely provides a list of them. And so if you want to practice on those, that would be good. Just as a side note, Python does have the ability to use something called a default dict. So that's in a different module or library. I believe it's itertools, or is no collections. Yeah. So with the default dict, I can actually store a key and a value, and if I try to edit that value before it's in place, it will automatically create a key with a default value associated with it. So let me do an example. So I guess I'll just do it right here. It's fine. So in here, I'll use the default dict, and I'm going to initialize the default dict with an integer type. So when I do something like, I don't know, apple plus equals 1, I'm actually editing the key. With a normal dictionary, this would cause a problem because I'm trying to edit a value of a key that's not already in the dictionary. So if I have, I'll call this my default dict, and then I'll just make my dict a normal dictionary. And if I try to run this, it's gonna have a problem because there's gonna be a key error. It's gonna try to look for apple and then edit the key associated with that, but that won't work. But if I make this my default dict, maybe if I know how to type, there is no error, and we can print out the value there, and it's 1 because it came to this line, it realized that that apple wasn't already in the dictionary, and then so it made it with a default value, hence it being called a default dict, with an integer being 0. And it added 1 to that 0 key, or key 0 value. So this is particularly helpful when you don't want to have to check if something's in there. Or if maybe you want to keep track of a list of stuff and you just want to append to a list, and it's a similar process, but instead of default dict of int, it would be a default dict of list. And you can use these to edit a key or edit a value associated with a key, but even if the key may not be in there, it'll just make one with a default value. So those can be helpful, but technically all this could be done by first just checking something like if key in my dict before actually doing the operation. Yeah.
Can you have a different default value of like 10 instead of being initialized to 0?
I don't actually think so. Maybe? I think actually maybe you could do that. Let's see. No.
You could do it with the lambda function.
Yeah. You could just have a lambda that assigns it, but yeah.
All the default dict constructor wants is something that if the function it can call to produce the default value. So that's why you pass.
Yeah, so int is actually a function that returns an integer.
Or like int parentheses 10. That work?
No.
I don't think so. Because that's not a function, that's actually returning from a function. This is the function itself. Int 10 returns 10, and you don't want that. You want something that it can call to do that.
So I wonder if you could do like a class in there and the class initialize the value.
Yeah, I mean, you probably could, yeah, maybe. I don't know, I've never tried. I usually just use it with a default value of 0 or an empty list. But yeah, so that is it for my presentation. Yeah, like I said, there's some more problems here if you want to work on those. LeetCode marks easy, medium, and hard. So the easy ones won't quite all be as easy as, duplicate checking, but they are going to be fairly simple stuff. So I would recommend trying a naive solution first and then seeing if you can do like a more advanced solution. But yeah, that would be my advice for that. Cool. Well, thank you.